There are places in the universe where time almost stops, where a single second could stretch into an eternity, and the very fabric of existence seems to bend to an invisible will. Imagine a clock ticking slower, not because its gears are jammed, but because it's caught in the titanic gravitational pull of a cosmic behemoth. Near black holes, gravity becomes so impossibly strong that time itself slows down dramatically. This isn't science fiction, it's a fundamental truth of our universe, known as gravitational time dilation. So, what exactly is gravitational time dilation? In simple terms, it means that time passes more slowly for objects in a strong gravitational field compared to objects in a weaker one. Picture two identical clocks, one floating freely in deep space, far from any massive object, and another placed near a neutron star or a black hole. The clock in the strong gravitational field would tick more slowly. If you could observe both, you'd see the deep space clock racing ahead while the other lags behind. To understand why this happens, we need to talk about space-time. Albert Einstein revolutionized our understanding of the universe by showing that space and time are not separate entities, but are interwoven into a single four-dimensional fabric called space-time. Think of it like a giant, flexible trampoline. If you place a small marble on it, it barely dents the surface. But if you place a heavy bowling ball, it creates a significant dip. This dip, in Einstein's theory, is what we perceive as gravity. Massive objects, like planets, stars, and especially black holes, don't just exist in space-time. They warp and bend it around them. The more massive an object, the deeper the dent it creates. And this warping of space-time directly affects how time flows. The closer you are to this warp, the stronger the gravity, the slower time moves relative to someone further away. Consider the hypothetical scenario. An astronaut ventures close to the event horizon of a black hole while their twin remains safely on Earth. When the astronaut eventually returns, they would have aged only a few hours perhaps, while decades or even centuries could have passed for their twin on Earth. This isn't just theoretical. Even here on Earth, GPS satellites in orbit experience time slightly faster than clocks on the ground due to Earth's weaker gravity at their altitude. Without constant correction, our navigation systems would be wildly inaccurate. This profound connection between gravity, time, and space completely rewrote the laws of physics. Before Einstein, Isaac Newton described gravity as a force pulling objects together. But Einstein's general theory of relativity revealed gravity not as a force, but as a consequence of the curvature of space-time caused by mass and energy. This means that gravity doesn't just pull things, it dictates the very rhythm of time and the geometry of space. It's a dance where the dancers, mass and energy, choreograph the stage, space-time, and in doing so, they also set the pace of the music, time. Einstein didn't just propose this idea, he predicted it mathematically, forever changing our understanding of the cosmos. His equations showed that time is not absolute, but relative, a concept that defied centuries of scientific thought. This profound insight allowed us to look at the universe not as a static backdrop, but as a dynamic, interconnected entity where everything influences everything else. From the minuscule corrections needed for our GPS systems to the mind-bending possibilities of time travel near cosmic giants, gravitational time dilation reveals a universe far stranger and more fascinating than we could ever imagine. It's a universe where the ticking of a clock is not universal, but intimately tied to the gravitational landscape it inhabits. It leaves us pondering. If time can be stretched and squeezed, what other fundamental aspects of reality might also be relative?